Hey there class, in this video today we're taking a look at another concept with respect to enthalpy. It's called enthalpy of formation, and what it is going to involve for us is another way for us to calculate or estimate, in this case, delta H of reaction at standard state. Now, what enthalpy of formation is it's the enthalpy change when 1 mole of a compound forms from its constituent elements that are in their standard states. And I have a good example of it down here, but pretty much it just represents the change in enthalpy when a substance forms. So you can see here NH3 ammonia is being created in this reaction, and it's being created from its constituent elements N2 and H2 in their standard states. And we'll get into what that means in a second, but for nitrogen and for hydrogen, that means that they're gases. It's also really important that we note here that it is the enthalpy change for 1 mole, which is why there is 1 implied in front of this, and why we have these weird fractions here. So even though when we first balanced equations we said we couldn't have fractions, and that's still true, when we're writing reactions that are for enthalpies of formation, for forming 1 mole of the compound, we really do want to make sure that we do have fractions if we need it. And so this right here is the enthalpy of formation for this reaction. So what it kind of is it's a specific type of reaction. It's a chemical change, a process that is occurring, right? And this is the enthalpy change for the formation, that's what the F means, at the standard state. And it's going to release 46 kilojoules for every 1 mole that is produced. So for this specific compound, this is an exothermic process, but occasionally it can be an endothermic process too, where to make 1 mole of a substance, it's going to be a positive value over here. And so what enthalpies of formations are the reference values that are going to exist for compounds or for elements. So we've talked about how it relates with compounds. Let's talk a little bit about standard state and how it relates with elements. So the standard state, right, that degree sign, and we've mentioned this briefly already, is the value that's measured in that standard state. So what that means is that they've measured the enthalpy change at these conditions, and that allows us to have this tabulated version of a bunch of different compounds where we can have a variety of different substances, but they were all measured at the same condition, so we can trust that would be accurate. If it's a gas, that means that the pressure is of 1 atmosphere. If it's a liquid or a solid, the substance, it's going to be whatever the substance's most common stable form at 1 atmosphere and 25 degrees Celsius is, and we'll talk about that in a moment. And if it's an aqueous solution, that means that it's 1 molar. I mentioned in a previous video that this is different from STP because the temperature that we use for standard state is 25 degrees Celsius. So just as make sure we have a note of that. Now, when it says it's the substance's most common and stable form at 1 atmosphere and 25 degrees Celsius, for H2O, right, as a liquid, that's water, okay? It's just going to be liquid water as its most common stable form. Some substances have more than 1 possible form. So carbon, for example, its most common stable form at these conditions is a solid, but it's also got this GR here. That means graphite, okay? Because the other form of carbon, which is not as common, is diamond. And so you would see S and then something like DIA here, okay? But the most common form is carbon as solid for graphite. But the thing I really want to pick up on is that any pure element, okay, at its standard state is given the enthalpy of formation of 0. And the reason why is this allows us to use it as a baseline, so that N2 from the previous example, because nitrogen is a diatomic, this is its most common stable form at these conditions, right? And with a pressure for a gas at 1 atmosphere, it's going to have an enthalpy of formation of 0 kilojoules per mole. So is the hydrogen that was in the previous question. So any of those constituent elements, anytime you see an element by itself in its most common stable form, okay, that's going to have an enthalpy of formation of 0. And that's going to play a role for us in just a moment. So I mentioned that we could use this formation data to calculate the enthalpy of reaction overall. And it is a really, really good estimate for us, okay? To do so, we use this rather ugly looking equation. So let's say we had this reaction right here, and we're calculating the standard enthalpy change for the combustion, which is just a type of reaction. Okay, so we're calculating this for this reaction right here. Well, what we're going to do is to measure the enthalpy of the reaction at the standard state, we're going to add up the enthalpy of formation of the product values multiplied by their mole amounts and subtract the enthalpy of the reactants, each multiplied by their mole amounts, and add it up. So this strange symbol here is the Greek letter sigma, meaning sum, okay? The N is telling us we're going to multiply each formation value by its mole amount that is in the balanced equation, okay? But where do we get these numbers from? They would come from a table, okay? Now there are times occasionally where you'd be given this value and you'd be asked to solve for potentially the enthalpy of formation of CO2 using this equation and other information, but we're just going to focus on how do we calculate this for the time being for right now in this video, okay? And so there is a table of values of this on Schoology. You would want to look for the standard enthalpy of formation table, and you'd want to look at what the value should be for CO2, for H2O, for C6H6, and for O2 as well. And then we're going to plug them in to our equation. And so if you were to go to the table on Schoology in AP documents, in Unit 4 and 5 documents, and see for standard enthalpies of formation, you would see this right here, okay? And what I mean by that is that we are taking the enthalpy of formation of each product. So I took the enthalpy of formation of carbon dioxide gas from that table, and I plugged it in right here, and I'm multiplying it by the 6 moles. And I'm going to add to it the enthalpy of formation of H2O liquid, not gas, which is negative 285.8 kilojoules per mole, and multiply it by 3 from this balanced equation. This is in its own set of brackets because I should solve this first. And then I'm going to subtract from that the 1 mole of C6H6 multiplied by 49 kilojoules per mole, which is its enthalpy of formation. And then we should be able to recognize that O2, that is a diatomic element. It wants to be a gas. That's in its standard state. This is going to have an enthalpy of formation value of 0 over here. And so now I can use this data and I can solve step by step for my delta H reaction. And so when we type this into our calculator and go step by step, we should get the following here, and then adding and subtracting those values together, we should get a final answer for a delta H reaction, of negative 3,267.4. Now, there are a few things that I really want to stress with this. There again will be times where you are given, for example, this value right here and asked to calculate what this is, okay? You always want to make sure you slow yourself down and have a really good setup, okay? So make sure that you've got the correct mole amount with the correct delta enthalpy of formation. Also make sure that you're doing products minus reactants. That's a big common mistake that people make. We want to remember that delta meaning final minus initial, right? Products are the final state, reactants are the initial state. It's also important that we don't forget about mole amounts. Oftentimes you might see this product answer written as kilojoule per mole, and I believe that in that case it's implying like per mole reaction within that context. Remember that pure elements are 0, and then be so careful that you don't forget just one negative sign, because it will mess up a lot of different components here, okay? So this is how we do these questions. We'll do some practice of this when I see you next. Please let me know if you have any questions. Thanks.